Hi everybody and welcome back. Now it's time to evaluate our model. Before doing so, we need to import some libraries. At first, HTML from ipython.display. Next, camera from celluloid. And last but not least, NumPy. After doing so, we load the model and place it on the GPU if possible. Let's define a variable called model, which will store our segmentation model with loaded weights. Let's use the most recent checkpoint, in my case that's epoch 97. After that, we use torch.device to copy the model to the GPU if CUDA is available, else we work on a CPU. Last but not least, all we have to do is to set our model to evaluation mode and copy it to the predefined device. Now it's time to implement the patch aggregation. Our model was trained in a patch-wise manner as the full volumes were too large to be placed on a typical GPU. However, we still want to get a result for the whole volume. The goal of patch aggregation is to split the volume into similar sized patches, then predict the segmentation for each patch, and finally merge all predictions back together. The pipeline is as follows. At first, we have to define a grid sampler which accepts a subject, a patch size, and a patch overlap, which is responsible for dividing the volume into patches. You can identify each patch by accessing its location attribute. Next, we create the grid aggregator, which accepts our predefined grid sampler to merge the predicted patches back together. After that, we compute the prediction on the patches and aggregate them by calling aggregator.add_batch, which accepts the prediction and location of the patch. Last but not least, we call aggregator.getOutputTensor to extract the full prediction. Typically, we can leverage the PyTorch data loader to perform the prediction in a batch-wise manner for multiple patches at once. Alright, at first we define an index IDX to define the validation subject we want to use. Let's use number 4. Next, we access the validation subject defined by the index, select its CT entry, and directly extract the raw volume by accessing the data attribute. We perform the same operation for the segmentation mask by selecting the corresponding label entry. Let us now define the grid sampler by using torch.io.inference.gridsampler. At first, we pass the full subject defined by our index. Next, the patch size we used during training, 96, and last but not least, a patch overlap of 8. Please note that the patch overlap is a hyperparameter, so feel free to play around with it. Using this grid sampler, we can now define the grid aggregator by using dio.inference.gridAggregator, to which we pass our grid sampler. Finally, let's define the PyTorch data loader for speed up. We create a variable called patchLoader, to which we assign a PyTorch data loader, which accepts at first our grid sampler and next a batch size of 4. You can of course change the batch size according to your hardware. Alright, let's calculate the prediction. At first we use with torch.no_grad to prevent PyTorch from storing the gradients. Next, we loop over our patch loader to extract the patches from the volume. Within the loop, we at first create an input tensor by extracting the raw ZT patches of our batch. Additionally, we directly copy them to the previously defined device. After that, we grab the locations of the patches within the volume by accessing their location attribute via torch.io.location. We are now ready to compute the prediction based on our input tensor and finally add the prediction to the aggregator by calling aggregator.addBatch, to which we pass the prediction and locations within the volume. Alright, let's run it. Once the prediction is done, we call aggregator.get_output_tensor to aggregate or merge all predictions into the final prediction of the volume. Perfect! Everything is done. We can finally visualize the prediction as usual. To do so, we at first create a matplotlib figure, which we directly use to create our celluloid camera object. Next, we take the argmax along the first axis of our output tensor to get the final prediction of our network. We can now loop along the axial slices. In fact, let us only plot every second one to decrease the plot duration. Within the loop, we at first visualize the current axial slice of our full volume. As usual, let's use the bone color map. Subsequently, we use numpy.me.maskedWhere to mask all values within the current slice of the predicted segmentation that are 0. Let us now plot this masked array as an overlay over the current CT slice with an alpha of 0.5 and additionally the autumn color map, as it yields a really nice red segmentation mask. Last but not least, we call camera.snap within the loop and create the final animation via camera.animate. Alright, let's take a look at the visualization. Oh, we somehow forgot to import matplotlib. Let's quickly fix this. Okay, let's try it again. Alright, perfect. Last but not least, all we have to do is to use the HTML function to convert this animation into an HTML5 video. Congratulations everybody, that's it. Please lean back and enjoy. Our model successfully segmented the liver and even the large tumor inside it. Thanks to everyone and see you soon.